In this paper, we explore different tactile representations of network data for blind or low vision or BLV people. This work is within the big vision of improving the accessibility of visualizations for BLV people. Visualizations are widely used to present data, taking advantage of the powerful human visual system. Sighted people usually can perceive information from a well-designed visualization easily. Unfortunately, BLV people cannot benefit from visualizations directly. Furthermore, due to the popularity of visualizations, many important information becomes inaccessible to them. Choi and his co-author developed a system that can retrieve the raw data from a visualization and then use the screen reader to read the numbers. Their nice work make it possible for BLV people to access the raw information. However, only simple visualizations are supported in their system, for example line chart, bar chart. Furthermore, representing data in its raw format is not an effective way to pass on information. The user may experience a heavy memory overload. Compared to information in raw format, tactile representation has the potential to preserve the visual information into a format that is accessible for BLV people. There are studies investigating different parameters for producing tactile visualizations. There are also studies comparing graphic tactile representations to text representation, that is Braille. However, these studies are again focused on simple standard statistic charts. In this paper, we focus on tactile representation of network data. Network data are widely collected. In a network, there are nodes that represent entities and links that represent relationships between these entities. Network visualizations are commonly used and well studied. However, to the best of our knowledge, there is no study on how to best represent network data in accessible format. We investigate this by first exploring the design options and then conducting a user study with 8 experienced touch readers on Swell papers. Swell paper is made of a special material. It swells along black lines and diagrams after being heated. The most familiar representation to touch readers should be in the format of text or Braille. With text, we can simply list the neighbors for each node. For example, here A is friends with C and D. We do the same thing for all nodes, and then use the Braille to create tactile representations. Apart from using text, we also consider more graphic way to represent network data. Node link diagrams and matrices are arguably the most widely used visualization for network data. We adapt these to representation to tactile format for the user study. Let us look at the matrix first. In a matrix, each row or column is showing one node. Here we are showing the node for A, C, and D. We use a circle at the intersection to indicate there exists a link between two nodes. Here we are showing the in-link between A and C. In addition to these standard designs, there are several design choices for creating a tactile matrix. A matrix usually has grid lines to help align rows and columns. Apart from making the lines go through the center of the cells, another alternative is making the cell inside the grid. We piloted these two representations with an experienced touch reader, and she clearly preferred the first option. A good order of rows and columns can help the user identify high-level patterns. We follow the recommendation from past research and use the optimal leaf ordering to calculate the order of rows and columns. We also use the Braille labels on the left for rows and on the top for columns. These labels are essential for participants to know which rows and columns correspond. We also use the spur wheel to mark the diagonal line with the texture distinct from the other lines. We expect this diagonal line can help our participant to understand the symmetry of the matrix. Let us then look at the node link diagram. Crossings are inevitable for creating node link diagrams. We consulted with an experienced transcriber about the ways of representing the crossings. She suggested introducing gaps to make it easier for touch readers to distinguish the individual lines. Another important design choice for node link diagrams is the layout. Force-directed or organic layout is the most widely used layout for node link diagrams. Alternative to the force directed layout, orthogonal layout has been tested to be preferred by sighted readers and required less memory load. We conjectured that touch readers would find these diagrams easier to navigate. We did not use technical terminologies in the user study. Instead, we used the friendships to explain the concepts. For example, in a node link diagram, each node is a person, and if there is a link between two nodes, that means these two people are friends with each other. From the literature, we identified 6 essential tasks for exploring network data. We measured both time and accuracy for performance. We also recorded self-reported difficulty and strategies from our participants. The first task is estimate the number of friendship links. This task investigates how different representations help the user to capture an overview of the data. We normalized the error rate with the answer from participants using the following formula. Close to 0 means more accurate, above 0 means overestimate, and below 0 means underestimate. We did not find statistic significance comparing different representations. Interestingly, in the node link representations, participants consistently underestimate the number. The reason may be that the lines representing links are not textually salient. For the self-reported difficulty, overall, this task seems considerably difficult for touch readers. The second task is how many friendship groups are in the social network. This task was looking at the connectivity of the network topology by identifying clusters. We used the same way to normalize error rate. We found the 2 node link diagrams were more accurate. Statistic tests revealed that node link diagrams were significantly more accurate than matrix in small data and text in large data. This is in line with the self-reported difficulty, which was also higher with the text and matrix. When analyzing the time, we aggregate the time of these 2 tasks, as participants were aware they were going to be asked task 2 when they were exploring task 1. We found participants took significantly longer with text than with the other 3 representations. Participants also reported to have relatively well-defined strategies for node link diagrams and matrices. They either identify closed groups or the bridge between groups. While in text, participants reported they could only make an educated guess. One participant also mentioned he tried to build a matrix representation in his head as he had just seen that in the previous trials. Some other participants tried but felt quite difficult to do so and commented, "It is overwhelming for me to think about all that." The third task is find the 2 people with sticky plasticine. Are they friends? All participants could complete this task correctly. We found the 2 node link diagrams were faster than matrix and text. Text was also faster than matrix. This is also occurred with self-report difficulty, where the node link diagrams were considered easier than matrix. When discussing the strategies, participants commented following the rows and columns in a matrix is not easy. The matrix is also considered to be too cluttered. Participants also feel the diagonal line sometimes distracted them. The next task is still looking at topology adjacency, which is find the 3 people with sticky plasticine. How many friends do they each have? We found the text was faster than the matrix. As discussed, the difficulty of flowing rows and columns in the matrix may slow down our participants. Self-reported difficulty was similar for all representations. The next task is looking at common connections. We asked, find the 2 people with sticky plasticine. Who are their mutual friends? We found the organic node link diagram and the text were faster than the matrix. Participants tended to feel more difficult with the matrix, but was not statistically significant. In the text, participants heavily relied on memory. They read along 2 rows and then identify the friends in common. In the matrix, participants traced down the column or row in parallel and found corresponding circles. The last task, we asked participants to find the 2 people with sticky plasticine, then find a path of direct friends connecting them. We found the node link diagram was significantly faster than text and matrix. Participants also found node link diagrams significantly easier than text and matrix. In both text and matrix representations, participants heavily relied on their memory to search the possible paths. In the matrix, participants also mentioned to use the spatial layout to guide the search. For example, look at E and H's friends, remember this, then say semi-systematically looking for links between these. In the node link diagram, a common practice is following the link directly heading towards the destination node. If it is a dead end, the participant then backtracked and tried the link most closely to the direction of the destination, following links in that direction until reaching the destination. We also asked participants to rate the understandability and imaginability of different representations. Unsurprisingly, the node link diagram overall had a higher rating than the text and matrix. One representative comment is, liked the node link representation, imagined the nodes as people. This wasn't true for the Braille list. There, they were just letters and numbers. We also asked participants to rank the intuitiveness and usability of these representations. Again, we found participants prefer node link diagrams than the text and matrix. Representative comments are, love these organic graphics. They make it so easy. This is how I would show someone what a social network is. Liked the regularity of the grid, made it predictable. Grid and right angles help me to make more memorable mental image. In this study, we found node link diagrams are the overall winner. They were faster and easier for the tested tasks. There is also little difference between the two different layouts. Participants performed unexpectedly badly with the matrix. Participants found it by far the hardest representation to understand. One particular difficulty was understanding that the matrix was symmetric and that the diagonal was a line of symmetry. Such information is immediately apparent visually, but not when explored by touch. Matrix was also complained to be too cluttered. Removing the line may improve the matrix representation. Surprisingly, we found text representation performed reasonably well. However, participant comments revealed that it placed a higher demand on working memory. It thus may have difficulty scaling to large networks. Interestingly, one participant reported that the textual representation led to a linguistic representation rather than a graphic image. Thank you very much for your attention. I'm happy to take any questions.